saw that the animal contribution of this diagram in quantum electrodynamics was given by the simple formula times the logarithm here. Okay. Remember this. And we saw that by using a representation of this as an integral in the complex plane which has the following form. Where C is the real part of the integration variable S was in this range. We have been able to rewrite this. This is a linear bounds representation. Rewrite this as a different integral minus s divided by the sine pi s squared times 1 minus s divided by 2 plus s times 1 plus 2s times 3 plus 2s, whereas this time d was inside this.
Okay, some probably know there are those called expense functions, the logarithms, which sometimes appear to loops, pre-loops. I mean, do you also have maybe Marx representation for that, or with this representation you are able to get everything?
With this representation, in fact, there is a more general one that we will see later, which contains the logarithm of special cases. We will see this just in a few minutes.
Okay.
But what was important going from this equation to this one was that we have here the mixing between the parameters of the integral, the masses, okay, and the variable x and y of integration. But here you see that there is a separation. In fact, you have a function that depends on s and the kernel of integration. Where the masses are excluded, not excluded, but separated. Okay? There is a minus s, of course, here. But you see that this minus s will give, in fact, the power, the expansion in powers of this. Also, logarithm. Since you remember that we found the logarithm by computing this integral. Okay? And it was also nice because when at the singular structure of this subject to know how to compute by closing the integration contour by Cauchy theorem the sum of all contributions which lead to these powers of the ratio of mass to the logarithm. But is it always true that we can perform this closing of the contour? Because we did it without checking anything about the integral. This is not, in fact, always possible. We will see this now. by considering general integral. This is the one I just spoke a few minutes ago, which is the following. Power minus s times the product here, g equal to 1 and of gamma functions. This is a j s plus j divided by the product of the same form with not the same number gamma functions. This is k. Okay. Where we choose C, which is always the real part of S, in order that it doesn't be at some pole of the integrals. Of course, otherwise the integration not be able to perform because the integral will be divergent. Okay. So C, the real part of S, is not at any pole of the gamma functions. So this is a very general class of integrals and of special function that can be represented as this Bell-bound integral. Now, let us define two quantities. The quantity delta, which is some j1 and kj minus some k equal 1 and say k. Okay? And the same quantity but with absolute values. I forgot to say that the AJ and CK are real numbers, but this one may be complex. And this may be complex also. Here it's real, but this is the ratio of masses. But in general, they use the division also for X complex. Now, there is a theorem that says that if delta is positive, once we're looking for this minus this result, then if you close the integration contour to the right, get a diverging asymptotic expansion. Okay, this means that in principle you cannot close the contour. You don't have converging series. This means that there is a non-zero value of your integral given by the Jordan lemma, you know? Okay? But it still makes sense in the sense that it's an asymptotic expansion that's diverging, okay? Divergent series, but often just by keeping the first few terms in a diverging asymptotic expansion, you have already a good approximate value of your integral, okay? If you close to the left, the series will be convergent. And of course, if delta is negative, is the converse situation. Okay? By closing the contour to the left, you have the direct asymptotic expansion, and to the right, the convergent series. Now, if delta is equal to 0, the last case is if delta equal to 0. In this case, you have both closing to the left or closing to the right series. Both theories are converging. One is converging in a disk modulus of the parameter less than the value, r, let's say r, and the other is converging outside of this disk. Okay? So you get two converging series by closing the contour to the left or to the right. So one series will converge for this is x modulus of x less than the value r. Okay? And the other, this is a disk. Okay? In the complementary outside of the disk. Okay, so this is a general theorem. Okay, now what is our situation here? Okay, this may be written as gamma s, gamma 1 minus s squared. Okay, this 1 minus s times gamma of 1 minus s equal gamma of 2 minus s. Therefore, I can replace this by the ratio of both. So this is gamma 2 minus s divided by gamma 1 minus s. And the same for the others. Gamma 3 plus s times gamma 2 plus 2s times gamma 4 plus 2s. And here I have 2 plus s, 1 plus 2s, and 3 plus 2s. Okay, so if I count, I have for delta s minus 2s, 0, minus s plus s, 0, 4s, minus s plus s, 0, minus 4s, 0. Delta equals 0, and we are in this situation where we can safely close the contour to the left or to the right. Okay? And we did it, in fact, remember, to the right only. And we obtain the following formula, just to recall you. Yes, I forgot to say that if alpha is positive, here, alpha was the same but with the absolute values. If alpha is positive, then in the case where delta equal to 0, The series are analytic continuation of one another. We also can find alpha is positive since it's equal to 4. So we were able to include the contour to find expressions, and we can perform resummations on these expressions to find the result in terms of special functions. Okay? Possible to do that, and after, if you know the analytic continuation properties of the special functions, you may, for instance, try to obtain AL of let's say mu tau, you may get AL of without long calculations. Okay. Let's see now how things generalize when we go to the most difficult case of the real calculation. Remember that we found the following bars of notation: 4 times alpha over 5 power 3, 1 minus 2 pi squared, c minus plus dt, ds, d minus I infinity dt and square over m1 squared power minus s minus t 1 over st, and a very nice symmetric function, which is of course due to the fact that the Feynman diagram is symmetrical. I over sine pi s, I over sine pi t, times gamma squared minus s, gamma squared minus t, divided by gamma 4 minus s, gamma 4 minus t, gamma 1 minus 2s minus t. I think there is a mistake. With c in minus 1 0 and d minus 1 0. So in this case, it is more complicated because you have two integrals. And what I want to show you is that, in fact, all what I just said for one-dimensional, one-fold million bound integrals will be generalized at the two-fold case. For this, we will consider the general two-fold million bound integral. Let's consider I prime 1 over 2 I C plus K D minus I infinity plus I infinity x minus s y minus t. Well, our product now is 1 and gamma functions having two coefficients s plus c j t plus b j divided by k equal 1 to n gamma of b k s plus d k t plus f k. Okay, well, as before, these objects are real numbers, and these may be complex as well as these. And we choose C and D in order that they do not touch the singular lines implied by the gamma function singularities. Okay? Now, you can define a vector delta this time, which is equal to sum j equal 1 m aj minus k equal 1 n ek. And the same for alpha with the absolute value. Now, 3 cases, 2, because the third I will not speak about it. If delta equals 0, 0, we are in the degenerate situation. You remember that in the one-dimensional case, for delta equal to 0, we have 2 series of notation, one obtained in the left, the other in the right. Here it's more complicated. There is no left, no right. Well, at least in this formation of things. And we will have several convergent series, not 1, 2, we may have 5, 4, depending on the region where they will converge and the type of integral that you find. Okay, it's more complicated. But this case is a degenerate case. Several convergent double series representation may be obtained. From this integral. Okay? And they converge in different regions of the parameters. Of the parameters value. Okay, the parameters are x and y. So, if delta now is non-zero, there is only one double series which converge everywhere, but in x and y equal to 0. Okay? Unfortunately, if you want, in the quantum field theory context in general, we are in delta equals 0 case. and we can see it here. Because delta is equal to this gives just doing the calculation for Aj and Ak to get this, because of the symmetry of the integral, we have the same answer for t. So I have 1 plus 1 minus 1. This is 1. Minus 2 minus 1. Minus 2 minus 3. Plus 1 minus 2. Minus 2 minus 1 minus 2, this is minus 1 minus 1 minus 2. And the same here by symmetry. Okay, so we are in the 0 case, several dimensional series will be obtained. But how can we obtain them? Okay, it's not as trivial as in the one-dimensional case. In the one-dimensional case, you just have to look at the poles to the right and poles to the left. But here, we are not in this simple situation. To show you, I will take a specific example, less difficult than this one, okay, which will be easier to explain things. We are going to consider the following simple integral. Gamma of s, gamma of t, gamma of 1 minus s minus t. So there is a mixing of the variables in this gamma function. It's very simple. You can check, of course, that delta is equal to 0. Okay, this 1 minus 1, 1 minus 1. And now with this, we will put C and D at some values, those that we want. I choose this one, but we will choose other. Of course, not capturing the singular points of the gamma functions, which are at the negative integers for this and negative integer for this. So, question, what is the singular structure of this integral? It is the following. If I perform a drawing in the real S periodic plane, the gamma S function has its pole. Where are the poles of the gamma function? Just say it. Yes? Where? Which place? Integers. Negative integers. Okay? Here. Minus 1, 0. Okay? And in T, the same way. Okay. Etc. Okay? Now, this 1 minus s minus t equal minus n with n in n, which is equivalent to t equal n plus 1 minus s. Okay. So when s is 0, t is n plus 1. In the case n equals 0, this is 1. S equals 0, t is 1. When S equals 1, in case N equals 0, T equals 0. Okay, so this is here. So we have a straight line like this. And in the N equals 1 case, the straight line is here. Okay, etc., etc., etc. This is the singular structure of our integral. And I said that C and D are at this value. Okay, so they are here. In fact, the point is here. There is C, D. Okay? So, where are the singularities from which we could extract residues from kind of extension of Cauchy theorem in this plane? Can you say that? Can you tell me which singularities will contribute to which series? Have you an idea of the number of different series of presentation of this integral? Just by looking at this, you could in fact. Have you an idea? No? How many? 1, 2, 3, 5? No, not 2. No, more. How many? A lot. It's not easy, of course, if you see it's the first time you see this. But if you have a look.
Isn't C and D in that range? Means 1.
For this integral, yes, of course, and this is extremely important, as you notice. Because, yes, it has not, this integral has not the same singular structure, okay?
But the range is the same?
The range.
For C and D is the same?
No, you see, it's negative, okay? I chose some positive values here. I chose it for the example, okay? This is dictated by QED, okay? I don't choose here. And this is an important point, okay? You have to check really the condition where the integrals may be, performed, because otherwise you will have the wrong answer. You will be able to compute it. It will give you some values, but it will be wrong. If it's not correct, if this range is not correct, so it is very, very important. In fact, if you have a look at the diagonal structure of this integral, you will see that it has the same as this one, the square here, which corresponds to this. Okay, so that in this integral, we should have C and D in this box. But in this one, I chose another. Okay? This is only a simple example to show you how to manage with two-fold many large integrals. But the question was how many? You see that this corresponds to different sets of poles. Okay? How many sets of poles can you see in this picture? There is one here. There is one here. And another here. Because all the other places, there are straight lines, but no crossing straight line section. You need intersections, okay? In order that both gamma functions, all gamma functions, in fact, these two, on S and T, diverge. Otherwise, doesn't give a contribution by complex analysis. Okay? So there are three sets. But in fact, there is a nice way to find them. To find them, you just draw an arbitrary line that goes through C and D. You draw this line, And you know that all the lines that cut our dotted line on one side of the line, the side is, both sides are separated by C and D here. There's one side here, another side here, okay, this line. All the lines that cut, that cross one side of this line, and that cross all the other lines that cross the other side, they are in one set together. Okay? This means that you see that this line, for instance, here is crossing this line, this line, this line, this line. So this, and this are singularities that are in one set, the same. But this line is also crossing the same side of the dotted line as this one, and crossing here. Okay? But this one is not correct. Okay? Because this one is a crossing of this line which crosses the dotted line here, and another line here which crosses the dotted line in the same side. Okay, so it's not, you don't take it in this set. And etc., etc., etc. So there is one set here that I could have done the exercise to the other side. And this would have given me this and this. So another set is the one which is here. Okay. And to find the last set, I said that this one was another set. You just have to perform a rotation of dotted line around C and D, the C and D point, and you will find all the possibilities. So try to do the exercise. For instance, you take this dotted line. You will find that this line is crossing the dotted line here, and all these lines cross to the other side. So this is one set, etc., etc., so etc., etc., etc. So, and if you do the exercise to the other side, you will find exactly the same as before. Okay? So, in this case, there are three series of notation, three double series of notation that converge in different regions. And it's easy, in fact, to compute them. Let's do this. So there is one set of singular points, which are, which one do they choose? Set one, okay. We choose this set. Okay, so it begins here at s equal 0 and t equal 1. This will be, for s, all the values possible are 0, -1, -2, -3, -4, etc. So this is -n for the abscissa. Now, for the y coordinate, it begins at 1 for s equal to 0, at 2 for s equal to -1. So, it will be 1 plus n plus something n, because you have an infinite points for each abscissa. Okay? So this is where we have all our points here by taking n and n in n squared. Okay? So we can do as in the one-dimensional case. We perform the change of variable s minus n, t plus 1 plus n plus n. Okay. Now, before doing that, let me write the other sets. Set 2, for instance, is this one in the square. So this is minus n minus n. Okay? And the last one, set 3, is n plus 1 n 1 plus n plus n minus n. Okay? And now from so we begin by calculating this one, which is simplest. Okay? Let's perform. So, set 2. We do this change of format. So, in the front, here, we will find x minus s plus n, y minus t plus n, gamma s minus n, gamma t minus n. Gamma 1 minus s plus n minus t plus n. Okay? Now, these objects are singular. Of course, because this is singular structure of this set. So, we write here the by perfection formula is as gamma of 1 plus s, gamma of 1 minus s, minus 1 to the power n, divided by s, gamma of n plus 1, minus s. We do the same for t, gamma of 1 plus t, gamma of 1 minus t, minus 1 to the power n, divided by t, gamma of n plus 1 minus t. And this one is non-singular. Stays like this. Minus s minus t. So you see that what we did here is to extract the singular structure because none of the gamma functions now are singular. The singularities are here. 1 over s, 1 over t. Okay? So we can apply the Cauchy theorem, Cauchy formula for the residue in 2 dimensions. This is simply the derivative if I define this as h of s times 1 over s t. The derivative, not the derivative, h of 0, 0, simply, which is x to the minus x to the power n, y to the power n, times this is 1, this is 1, this is 1, this is 1, minus 1 to the power n, minus 1 to the power n factorial, factorial n, minus 1, divided by gamma of n plus 1, gamma of n plus 1, which is n factorial. Okay? N factorial. Gamma of 1 plus n plus 1. Therefore, prime equals sum from n equals 0 plus infinity, sum n equals 0 plus infinity, x to the power n, y to the power n, with minus signs, gamma of 1 plus n plus n divided by n factorial, Okay? In fact, there is a subtle point to know the sign, the overall sign of this. Because when you do Cauchy theorem, you know that when you close the contour to the right, you have plus sign, and when you close the contour to the left, you have plus sign here. Okay? How do you know that? In fact, what you have to do for this is to consider your set of points and the line that you chose. Now, by convention, all the lines that cross this part of the dotted line are called F2, F1. And this F1 with F such that R F, where A is the matrix, equals J, J and S T. So here we see that the lines that cross are those corresponding to the S variable. So it will be F1 will contain S and F2 of course T. So that is trivial. So A is equal to 1, 0, 1, 0. Okay? And this is the value of the determinant of A, which gives the sign. That A equal 1, therefore the sign is correct here. You don't have to add the minus sign. Okay? For more details, I'll give you this reference. Journal of Mathematical Physics. 53 03508 012. If you want to know more about this, because this is a very trivial case. In general, it may be more complicated to obtain the A. It's not so easy. Okay. So we have determined that our integral is expressed like this, but where does it converge? Okay, because we know that there are two others. It's not the only series. So to know where this converge, we have to you have to use the so-called Horn theorem. It is important to know where these objects converge. Why? Because in general, here you have ratio of masses. So you have values, phenomenological values for these masses. So it's important to know which series is the correct one, considering the values of the mass that you have in your Feynman diagram. So it's important to know that. So a double series of the form sum over n equals 0 plus infinity, sum n equals 0 plus infinity, a m n x m y n is called a Horn series. Horn series if am plus 1 n divided by n, which is f, small f, yes, m n by definition, and j m n equals a m n plus 1 divided by a m n are rational functions. Okay? This is the case. This means that you can rewrite them as polynomial divided by r, another one, and this q and n divided by s and n. So P, Q, R, and S are polynomials of the P, Q, R, and S. In our case, it works. Okay? Why? Because when I'm doing this calculation of this by this, the gamma function will cancel thanks to the property that gamma of x plus 1, x, gamma, x. Therefore, at the end, we only have this, because we cancel between the numerator, this cancel between the numerator and the denominator. So, x here is 1 plus n plus n, and here it's n plus 1, here n plus 1. So at the end, we are in this case. Okay? So our series, and in general in quantity theory, the series are of Horn types. Not always, but very often. Now, if I define definition f of m n equal to the limit when theta goes to plus infinity f theta n and j m n equal to, let's say, therefore j. Then you compute this, and you will find that the region of convergence associated to your Horn series in the case which interests us, which is the one where P, the degree of P, and R, the degree of R are the same, as well as Q and S, because there are other cases. You find that P equal R and Q equal S, then the region of convergence is C inter D, T, where C equal x, y, so that x is less than 1 over the square value of f 0, 1, 0, and y 1 over j 1, 0. Now this is 0, 1. This is C, which in general is easy to compute. And another which may be more involved, and D is the same, but for all m and n in R2 plus, we have x less than 1 over f n n n y less than 1 over j n n. Okay, this is not so easy to find sometimes, complicated integrals. So this is bound theorem. Okay, now we can apply this. So we have A and N equals to -1 and -1 N, gamma of 1 plus N plus N, divided by gamma of N plus 1, gamma of N plus 1. Therefore, f and n equals m plus 1. So exactly this with m plus 1. So this is minus m plus 1 gamma of 2 plus n plus n divided by gamma of n plus 2. I won't write the n things because they will cancel. Okay. Divided by this one, which is times -1 to the power n times gamma of 2 of 1 plus n plus n. And here I have gamma of n plus 1. Therefore, it is equal to this with this n plus 1. This with this gives 1 plus n plus 1 plus n. Okay? With the minus sign. By symmetry of our series, we get directly the value of j and n is equal to -1, 1 plus n plus n divided by n plus 1. Okay? So it's trivial to get these limits.